Welcome to the deep dive. Today, we're tackling something totally fundamental. I mean, you feel it every single day, but maybe don't stop to think about how it works. We're talking about heat.
Yeah, so our mission for this deep dive is pretty straightforward. Figure out how heat gets made, how it moves around, and how we actually use it. We're going to trace the energy changes from giant space reactors down to what's happening inside your own body right now. We got five main ways heat gets produced to look into, but let's start with the big one, maybe the most basic question for you listening. What actually is heat?
It seems simple, right? But getting this clear is super important. Heat, or what scientists call thermal energy, it's basically energy from particles, atoms, molecules moving around, vibrating. The faster they jiggle, the more thermal energy they have.
Yeah.
Simple as that.
Okay, but we need to be careful here. Heat isn't the same thing as temperature, is it? Because we use those words kind of interchangeably sometimes. That's a really key distinction. Temperature just measures the average energy, like how fast the particles are vibrating on average. Heat is the transfer of that energy. It's energy moving on the go from where things are vibrating fast to where they're vibrating slower.
Right, like imagine a really busy dance floor next to a quiet corner. The energy, the movement spreads out from the busy part to the quiet part. Heat's kind of like that flow.
Exactly. And it always goes one way, naturally, from the warmer thing to the cooler thing. Always. Until they kind of even out. We call that reaching thermal equilibrium. Same average speed for the particles in both things.
Okay, let's make that real. Think about this. You drop a metal spoon into a really hot bowl of soup. Why does the spoon get hot so fast? It wasn't hot to start with.
Perfect example. That's conduction. The super energetic soup particles bump right into the slower spoon particles at the surface. Wham! Energy gets transferred. The spoon's particles start vibrating faster and faster, and pretty soon the spoon's just as hot as the soup. Equilibrium. So now let's dig into what gets that energy moving in the first place. Where does it originate? Let's start big, really big.
You mean the sun, the ultimate space heater. But the heat we feel here doesn't start as heat up there, does it? It starts with something else.
That's right. Deep inside the sun's core, the pressure and temperature are just, well, insane. It forces hydrogen atoms to smash together and fuse, forming helium. That process, nuclear fusion, converts a massive amount of nuclear energy into other forms. It's the engine driving everything.
And we're not talking a small reaction here.
Yeah.
The scale of this energy release is just mind-boggling. How does it keep going?
It's the sheer density and pressure cooker environment. You need temperatures like 15 million degrees Celsius to force those hydrogen nuclei, which normally push each other away, to actually fuse. When they do, boom, energy release.
But wait, if the energy is released way out there in the sun's core and space is mostly empty, like a vacuum, how does that energy get all the way to Earth to warm us up?
Crucial step. The nuclear energy first changes into radiant energy. Think light, infrared, UV rays, electromagnetic waves. This radiant energy can zoom right through the vacuum of space, no problem. It only turns into what we feel as heat, thermal energy, when it actually hits something here on Earth. The air molecules, the ground, your skin. That's when the vibration happens.
Oh, okay. So on a cloudy day versus a sunny day, the clouds aren't stopping heat itself. They're blocking the radiant energy from reaching us. They stop that final conversion step down here.
Precisely. It stops radiation before it can excite the molecules on the surface. A neat distinction, yeah.
Definitely. Okay, let's pull back from space now and look at something more down to Earth. The main way we make heat ourselves, fire, combustion.
Right. We're shifting from smashing atoms to, well, basically breaking chemical connections. Combustion is a chemical reaction, usually a rapid one, with oxygen. A fuel could be wood, gas, coal, whatever, reacts with oxygen, and the energy that was stored inside the chemical bonds of that fuel gets released, mostly as heat, but also as light.
And how efficiently that happens really matters, doesn't it? Like burning a log versus burning gasoline. Same basic idea, but totally different results in terms of heat and, well, other stuff.
Absolutely. It comes down to energy density and the molecules themselves. Gasoline's got these complex hydrocarbon chains. When you break those specific bonds, they release way more useful energy for the same amount compared to, say, the cellulose in wood. The type of fuel dictates the heat output and also the byproducts like smoke and pollution. It's all in the chemistry.
Fascinating how much chemistry shapes our energy world.
Yeah.
Okay, let's switch gears again. We've done cosmic fusion. We've done chemical reactions. What about just movement, mechanical source?
That takes us right to friction. This is where mechanical energy, the energy of motion, gets turned directly into thermal energy.
And this one's cool because you can feel it right now.
Yeah.
Seriously, try this. Rub your hands together. Fast. Really fast for like 10 seconds. Go on.
What do you feel?
Heat. Definitely warmer.
See? You just converted the kinetic energy of your moving hands straight into heat. And the way it happens is kind of messy on a tiny scale.
Yeah, it's not like smooth surfaces sliding perfectly. Even things that feel smooth have tiny little bumps and ridges, right? Microscopic ones.
Exactly. When you rub them, those little imperfections catch and snag. They collide, forcing the molecules right at the surface to vibrate much faster. That faster vibration is the heat. More resistance, more snagging, more molecular chaos.
Yep.
This means more heat.
And this isn't just, warming your hands. It's huge in engineering. Think about car brakes.
Oh, yeah. When you slam on the brakes, you're using friction between the brake pads and the discs, the rotors, to stop the car. You're basically converting all the energy of that heavy moving car, the kinetic energy, into pure raw heat. A lot of heat.
And the engineers have a massive job not just making the brakes stop the car, but figuring out how to deal with all that heat, right? They need cooling systems because if the brakes get too hot,
They fail. Big time. So managing that heat, getting rid of it safely, is just as important as creating the friction in the first place. It shows how a useful conversion can become dangerous if you don't manage the heat byproduct.
that idea of managing heat, especially unwanted heat, links nicely to our next source, electricity. This is probably where a lot of heat in our homes comes from, device-wise.
For sure. Things like toasters, electric kettles, space heaters. We are deliberately turning electrical energy into thermal energy.
How does that work? What's happening inside the wires?
It's often called the Joule effect. When electric current, the flow of electrons, goes through something that resists that flow, like a wire or a special heating element, the electrons bump into the atoms of the material. These collisions make the atoms vibrate more intensely. And that vibration, again, is heat. It's electrical energy becoming thermal energy because the material is fighting the current.
You mentioned resistance. So if you want a lot of heat, like in a toaster, you need something with high resistance. What do they use for that?
Yeah, exactly. Engineers use specific materials, often alloys like nichrome, which is nickel and chromium mixed together. Nichrome resists electricity really well, and it can get super hot without melting or burning up easily. It's designed specifically to turn electricity into heat efficiently, or, well, inefficiently from an electrical standpoint.
Okay, that brings up a cool question then.
Eh.
Toasters and heaters are designed to make heat. But what about other electrical things in your house? Which ones are trying really hard not to make heat? Where is heat a problem?
Oh, loads of things. Think about your computer's processor, or the big power lines carrying electricity across the country. In those cases, heat is pure waste. It's energy that was supposed to be doing calculations or just moving from A to B, but it leaked out as useless thermal energy instead. It's tied to the laws of thermodynamics, really. Every time you convert energy from one form to another, nuclear, chemical, electrical, whatever, you always lose some as waste heat. Always.
Wow. So the exact same process, electrical resistance causing heat, can be the whole point of a device, like a heater or a major headache, like your phone getting hot when you use it too much.
Precisely. It's all about whether that thermal energy is intended and useful or just an unwanted side effect.
Okay, last source. Maybe the most complex one. Us, the human body.
Yep. We are walking, talking furnaces. Our bodies work constantly to maintain a core temperature around 37 degrees Celsius or 98.6 Fahrenheit. And how do we do it? It's chemical conversion again, metabolism.
Right, we eat food, which has stored chemical energy.
Yeah.
Our body breaks that down.
It's through metabolism, yeah. And it converts that chemical energy into two main things. Mechanical energy, so we can move our muscles, run around, talk. And thermal energy, to keep our core temperature stable. It involves complex processes, breaking down molecules like ATP, releasing energy. A big chunk of that energy release immediately shows up as heat.
So we're constantly generating heat just by being alive. But I've heard the human body isn't very efficient at the movement part.
That's true. Surprisingly inefficient, actually. When your muscles turn chemical energy into actual movement, maybe only about 20–25% of the energy goes into the work itself. The rest, the huge majority, like 75–80%, is just released straight away as heat. That internal heat production is vital for staying warm, but it also means we often have too much heat.
Which leads to that slightly weird question. If we need heat to survive, why do we sweat so much when we exercise hard or try to get rid of energy we just made?
Because exercise ramps up your metabolism like crazy. Your internal engine is going full blast, generating way more heat than usual. If you didn't get rid of that extra heat, your body temperature would shoot up to dangerous levels very quickly. Sweating is our built-in cooling system. When sweat evaporates off your skin, it uses up a ton of energy. It's called the latent heat of vaporization. It literally pulls thermal energy away from your body, helping keep that 37-degree balance.
That's amazing. Such a delicate balancing act.
Ah,
Okay, let's quickly pull these 5 sources together. Maybe group them by where the energy
good
starts.
idea. So the sun and fire, they both start with stored potential energy, right? The sun taps into nuclear energy, converts it to radiant energy through space, and then finally thermal when it hits something. Fire uses stored chemical energy in the fuel, releasing it as thermal and light energy.
Okay. Then we have the motion and electricity ones.
Hmm.
Friction is about movement converting mechanical energy into thermal energy because of resistance.
Yep. And electricity uses the resistance in wires, the Joule effect, to turn electrical energy into thermal energy.
And finally, the body, which is kind of a mix. It takes stored chemical energy from food and turns it into both thermal and mechanical energy through metabolism.
Great summary. Now let's put on our energy detective hats. When you look at any technology, especially newer stuff, you can usually spot which of these conversions are happening.
Like an electric car. We know it uses electricity for the heater that's electrical to thermal. But where else do these conversions pop up?
Oh, they're still there. You still get friction mechanical to thermal from the tires on the road, and definitely in the traditional brakes if it has them. Though many electric cars use regenerative braking, which tries to capture some of that motion energy back as electrical energy instead of just wasting it all as heat from friction.
Hmm.
And don't forget the battery itself. Charging and discharging it isn't perfectly efficient. There's resistance inside, so it generates heat that's waste heat from an electrical process that needs careful management, or the battery could overheat.
Wow. Okay, so understanding these conversions isn't just school stuff. It actually helps you see how efficient things are or aren't. So here's a challenge for you, our listeners. Be an energy detective for the rest of the day.
Look around where you are right now. Try to spot maybe three things, three objects or systems that are either making heat on purpose or giving off heat as waste. And ask yourself, what's the main point of that heat? Is it useful, like from a radiator? Or is it just leaking out like the warmth from the back of your TV?
Maybe it's the warm air coming out from under your fridge that's heat being deliberately moved out of the cold part. Or maybe you feel heat escaping around a window frame that's waste, poor insulation. Knowing the energy change helps you spot where energy is being used well and where it's just being wasted.
Yeah, understanding these basic conversions really is the foundation for thinking about energy efficiency, thermodynamics, how we use resources. We always want to maximize the useful energy, the light from a bulb, the movement from a motor, and minimize the useless waste heat that just escapes.
Which brings us perfectly to our final thought for you to chew on. We've seen that heat is made in all these ways, often as a side effect, sometimes as waste.
So here's the provocation. If pretty much every useful thing we do with energy, from making electricity to running a computer, creates some waste heat, how does that fundamental inefficiency, that guarantee of thermal waste, force us to change our thinking? How does it impact how we design everything, from power plants to tiny gadgets, especially if we want a more sustainable future? Maybe the challenge isn't just finding new energy, but also figuring out how to stop losing the energy we already have as heat.
Something to think about. Keep noticing those jiggling molecules and keep diving deep.